Greetings, and welcome to a lecture on threads. Alright, buckle in. This one's going to be a little bit long. There's a lot to talk about, and while I do generally like to avoid the pure lecture scenarios, there's unfortunately not much room to avoid that on this one. Again, why are we going to be doing threads? Well, we want to be able to use the full power of the CPU. Got my CPU monitor up here, as you can see, just standard idle utilizations, sub 10%. Now, if I run this threaded code, and it behaves itself, which it didn't right there. So first things first, since it's come up, this code's very random. Like, when you run this, it might go for 83 cycles, it might go for a few hundred cycles, it might go for a few thousand cycles. I do have it hard configured so that at 10,000 cycles it will self-terminate, because if it runs much longer than that, it starts potentially causing memory problems with Eclipse, especially with the amount of data it's spamming out to the console here. If at any time when you are running this code, if you think it's getting too much for your computer, remember you can click on the stop button here to force terminate the execution. Now, let me try this again and see if it'll actually behave. There we go. It's actually running now. And you can see now my CPU utilization is around 30 to 40%. But much higher utilization than typical. And it's also hitting all the CPUs, even though we've only got a total of 4 threads, the main thread and the 3 threads that I spun up. And there we go, it took 4,000 cycles instead of 80-ish cycles this time before the program locked up. And don't worry, we'll talk about what that means here in a moment. And you can see the CPU utilization spike that I had from having the threads. And I would not have this spike if this wasn't threaded code. If I was just simply counting up to 1,000 or counting up to 2 billion or something like that, it would have a small spike, of course, but it wouldn't look like that. So let's talk threads and how this works. So there's 2 core intents behind this file here. Intent number 1, showing the syntax of threads. What do you need to do to set up a thread in Java? How do you start a thread? What are the ways you can safely terminate a thread, etc., etc. That's goal 1, showing the syntax, the very basic syntax, mind you, behind threads. Goal number 2 is to illustrate the issues with sharing data between threads, and one very specific type of thread error that you can run into, which is called the race condition. So for the first round, we're just going to take a quick look at the syntax, not necessarily worrying too much about what is being done, but more of how are we doing it within the context of threads. And then after that, we'll go back over the code again to take a look at it in terms of, okay, what exactly are we doing? What is a race condition? And how are we triggering this potentially? First things first, for threads, you must either extend the thread class or you must implement the runnable interface. Now, typically speaking, you don't do this on main and pretend this is main and not main lecture. Typically speaking, you would not extend threads like this on main. You would have another class or another object that extends thread or implements runnable, and that's where you would have your thread code running. But to keep things simple for the demonstration, I'm doing it this way. It's not incorrect, mind you, but from a more proper software architecture point of view, you would typically not do it this way. I would have a separate class that I would extend thread on, and main would purely be my class I use to launch the program. None of these variables have anything to do with the actual syntax of threads, so we're going to skip over them for the moment, and we're going to skip all the way down here to line 30. A thread has to have an instance of an object. You cannot launch a thread off of a static instance. I would not be able to call main lecture.start. That's not going to work. You have to have an instance. And so I've got main lecture test1 equals new main lecture. So I am creating an instance of main here. And then in order to start a thread, you call the .start method, not the .run method, which we will take a look at here in a moment. In order to start up a thread, we call .start. Now, this is not your typical function call. Remember, ordinarily, when we call a function, the flow of execution goes into that function, and that function has to completely finish before flow of execution returns back to the calling point, and then flow of execution continues on. That's not how start method works. We call the start method, and then we immediately move on to the next line of code. There is no delay. You call start, it's going to start up the thread, and then while the thread is starting up, flow of execution is going to move on to the next line. So these will not block anything. Obviously there is some time involved. There will be some measurable amount of time spent in the start method, but flow of execution is just going to keep on going. That is important. Jumping down quite a ways, down to line 101, we have got the run method. You do not ever directly call run. If I directly call run, it will work just like a regular old method or function. It's not going to be a thread at that point. So you should never directly call run. You always use .start to start a thread. And eventually, run will be called. So when you call .start on a thread, at some point, the run method is going to be called and will start executing. Once the run method ends, so down here we've got the closing curly bracket for the run method. Once you reach this closing curly bracket and the run method goes out of scope, the thread is what's called dead. It will no longer register as being a live thread. It will be a dead thread. That does not mean the object goes away. It just means that the thread itself is no longer running, but the object that thread was attached to is still going to be there. It's still going to have all of its data, which is important. Sometimes that's what you want. You rev up a thread, let it go, and then once the thread's finished, you go back to that object and say, hey, give me the data that you generated or calculated or whatever while you were running as a thread. So again, sequence here. I create an instance of the object, assuming that object either extends thread or implements runnable. So I create the instance, do whatever setup I want to do. Again, this has nothing directly related to threads here. Start the thread with the .start method. That will, at some point, cause the run method to be called. Once the run method is finished, the thread is considered dead, but the object will still exist. And when you call the start method, this will not block flow of execution. As soon as the thread is started, it will continue on with the flow of execution in the main thread. This is important because you are generally going to want to have some way of pausing in the main thread to ensure that the other threads that you have started up have finished. And this is where the complexities of threads get into, because there is no hard, fast rule to this. Why did you spin up the threads? What are they doing? What is the architectural reason as to why you've got threads running in this code? And the answer to those questions is going to determine, do I want to use joins? Do I need to use a while loop to test if it is alive? Are these fire and forget? Do I just fire up these threads and then don't worry about them because they're off doing their own thing that I don't care about? Or at least not immediately. It's like, what is the architecture behind these threads? There is unfortunately no hard, fast answers here on how to do this. The two most common methods. One is to use join, and I've got this all commented out because I do not, in fact, want to use join here. That would be the incorrect option for this scenario. Join blocks the flow of execution. So if you have object.join, that means flow of execution will stop here in the main thread until this thread is done, it's no longer alive, then flow of execution will continue. If you call .join on a thread that is already dead, nothing happens. It's just like, oh, okay, yeah, that thread's no longer alive, so I can keep going. But otherwise, as long as this thread is alive, when you call .join on it, basically flow of execution will stop here on the main thread until this thread, has finished executing, and then flow of execution will resume. So if you've got the scenario for this might be, what if I want to pull down a web page? For whatever reason, this program needs to pull down information from a web page and then process that information, or some sort of URL. Maybe I'm pulling down an image from the web to display. Perfectly logical and reasonable thing that you would actually want to do. So, but that takes time. It takes measurable amounts of time to open up a WebSocket, go out to a URL, grab the data, download the data, depending on your connection speeds, and then wrap up the connection. And so in that scenario, I might use a join. Start up the thread, say, hey, go fetch this resource out there on the web, and then call .join while I'm waiting for that to finish. The other way that we can do this, and it's the way that I'm using for this program, is to check is alive. As long as the thread is still running, in other words, the run method hasn't finished and gone out of scope, the thread will report itself as being alive. And so here, what I'm doing is I'm saying, okay, while any of these threads are alive, because remember, OR conditions, as long as one of these is true, the whole thing evaluates to be true. So as long as any one of these threads is alive, continue doing stuff while the threads are doing their thing. In this particular scenario, I do need my main thread to be doing stuff while the threads are also doing their stuff. And so having a while loop, I'm just constantly asking, hey, are you guys still alive? And then once they're no longer alive, going through and continuing on with whatever else needs to be done. I'll be coming back to this. And that's it as far as the simplest of syntaxes for threads. There's a lot more that goes into fully utilizing the power of threads, but we are keeping things relatively simple. Again, to review the syntax, so there's a lot of moving parts here. Your class has to extend or either has to extend thread or implement runnable. In order to start a thread, you have to have an instance of an object. So I'm declaring an instance of an object. You do not call the run method directly. You call the start method, which will then be responsible for calling the run method. So you call .start to start the thread. And then you have to have some way for the main thread to recognize when its children threads are finished. You can either use .join to wait for the thread to finish and continue with execution, or you can check is alive if you need your main thread to be going off and doing other things. The run method is what will eventually be called when you start a thread. And once the run method finishes, once you reach its closing curly bracket and the run method is now out of scope, then the thread is considered dead. You cannot restart a dead thread. Keep that in mind. Also, some other just sort of minor nitty-gritty points. Each object can only be started once. So if I want 3 threads running, doing the counting, sharing the work between counting up to 1,000, I need to have 3 separate objects. If I try to change this to just calling start 3 times on test 1, basically that will never break. It will just count up to 1,000 and be done. It will never trigger the race condition because there's literally only one thread counting. We can see this by if we take a look at all the counting information here. You notice there are no numerical breaks. Obviously, the ID is 1. That's to be expected. But there are no breaks in the number chain. That's because there's only one thread. You must have separate objects if you want to have multiple threads running. So that covers the syntax. Now, what is this program actually doing? Again, this is not a program you would ever actually write. This is a purely theoretical program just to explicitly demonstrate sharing data and race conditions. So the idea here is that we have a value and we want to count up to a target. And then once these 3 threads have worked together to count up to this target, they will end. What we're actually doing is kind of nonsense, but this is a valid scenario. You might have some massive data processing that you need to do. Maybe you've got several gigabytes worth of data in a file that you need to read in and process and do some math manipulations to. Very much a valid situation for spinning up some additional threads to fully utilize your CPU power. So what we have here, the static variables, remember static is not unique to any one specific instance of an object. There's only one copy of any of these because they're associated with the namespace of main lecture, not a specific instance. So it doesn't matter whether I have 3 instances of main lecture or 3,000 instances of main lecture. There is one value, one target, one force kill, one R&D. That's it. Now, this here, the char ID, this one is a class variable and is unique to each instance of main. I'm going to jump down to run here for a moment because I want to talk about what are the threads doing and then go back up and look at all of the ancillary stuff in the main thread that's helping monitor this. So again, the idea here is that we are just going to spin in a while loop until we have counted up to 1,000. So we're going to take this shared data. Again, remember, main lecture.value is shared data between all 4 threads. Remember, we have 4 threads. We have the main thread. Anytime you start up a program, that's a thread. So we have the main thread plus the 3 additional threads that we are going to spin up to do the counting. So we have 4 threads. 3 of the threads will be changing this value, and then 1 thread, the main thread, will only read it. We've got sort of an inverse scenario with main lecture.forcekill. Only 1 thread, main lecture, the main thread, is going to change this value, and the remaining 3 threads are going to only read this value. So we have main lecture.value. Going to increment it by 1. We're going to print it out to the console. And then we're going to check, is our value equal to the target? And if it is, we're going to break. And then this actually is related towards ending the thread, so we'll come back to line 115 here. So the idea is each of these threads is going to increment it by 1, print the value out, check to see if it's time to stop, and then repeat. And this is where we can have our race condition. Because each one of these lines can be done in turn, or just randomly intermixed in with each other. So thread 2 could come in, increment the value, print it out, and this could be, so let's say thread 1 and thread 2, sorry, let me rephrase this. Thread 1 and thread 2 have executed this if statement. Value is value equal to target. Well, the value is currently 999, so no, that's not true. So they're going to continue on, but they pause here. So thread 2 and thread 3 are about ready to execute this line of code. Thread 1 comes back in and executes this line of code. Now the value is 1,000. And so when thread 1 reaches this if statement, it's going to break. So, okay, wait. Our value is equal to the target. I'm going to break out. So thread 1 breaks out of the while loop and dies. Remember, thread 2 and thread 3 are still on this line of code. So now thread 2 resumes. Value plus equals 1. Oh, now value is 1001. 1001 is not equal to the target. So we're just going to keep going. That is a race condition. It's also very random if it's going to happen. If I run the code again, oh, I'm glad I caught that on camera because that is one of the fastest lockup times I've had yet. 34 cycles. So this whole thing had to run 34 times before this triggered. If I didn't have all the other stuff that we're going to go take a look at here in a moment up in main, I would have had to have run this program 34 times before it locked up. Or it could be several thousand times before it locks up. Or it could run for 10,000 cycles and not lock up. This is where trying to debug race conditions like this can be really frustrating. Like here, took 2,392 cycles before locking up. Imagine for a moment that you have a bug that only has a 1 in 2,000 chance of actually showing up. This is why threads are painful, and you have to be very, very careful with your architecture to try to avoid issues like this. Okay. Let's hop back up to main and take a closer look as to how the main thread is initiating and managing things. So, as I mentioned before, we're creating 3 instances of main lecture, test 1, test 2, test 3, and I'm giving them all a unique ID solely so that way we can see who's printing what to the console. And then we are starting up the threads. So we have test 1 start, test 2 start, test 3 start. And if I go, let's see here, there we go. So here's a new startup. And you can see how the numbers are just kind of jumping around all the place. So we have thread 1 prints out 1, then it prints out 3. Then thread 2 prints out 2. Then thread 1 prints out 4. And it's like 1 and 2 just sort of toss the number back and forth for a long time until finally we have thread 3 printing out 19 and thread 1's on 94. So you can see how the threads are just completely desynced from one another. By the way, you've got no real control of this over this. Once you spin up a thread, the order of operations, like how the threads interleave their instructions, yeah, think back to that first video that I had you watch. You are not controlling that, nor are you going to be able to guess as to what incarnations the CPU is going to be doing with your instructions. All you can assume is that your instructions will be randomly interwoven between each other. And then 3 gets to go for a while. So 3 goes from 19 to 96, and then 3 gets to go a bunch of times. Then we're back to 1. Now we're trading back between 1 and 3. There we go. We finally got back to 2 at 84, while 1's on 144, so on and so forth. So it's just an interwoven mess. So we've started our threads. They are running. But now we need a way for our main thread to monitor what's going on. And so we've got our while loop here. We're just constantly asking the question, hey, is any of the threads, sorry, make sure I'm saying this correctly, are any of the threads alive? As long as there is one thread alive, I need to keep doing stuff. And here is where I'm trying to detect, has the race condition happened? In other words, if the main lecture dot value is greater than main lecture target plus 10, I put the plus 10 in there just sort of as an arbitrary check, just to make sure it's like, hey, yeah, did you really go overboard? And if the answer is yes, okay, well, the answer is yes. And if that is true, I need to try to terminate the threads. Now, there is no officially supported way to kill a thread in Java. There is no kill or terminate command. There are a couple of different ways that you can do this. One way is to call interrupt on a thread. That will put the thread into an interrupted state, which you can detect and then take appropriate actions with. This is the interrupt method is very useful if you have threads that you know are going to be sleeping. Like you've started up a thread and you needed to be awake, or you need to have that thread existing, but not necessarily doing something at every single given moment. And so when you need to put it to sleep or wake things back up, you can tell the thread, hey, interrupt, and detect that and take appropriate actions. The other way is by having some sort of value that you can set that will cause the thread to end. So I've got the force kill boolean. If I set that to true, then that will cause this portion of the while loop to no longer be true, because not true is false. And so that will cause the while loop to fail. And so that is very important to keep in mind when you're setting up your threads, is how do I expect these threads to terminate? Do I need to be responsible for terminating? Does the main have to be responsible for terminating these threads? Or are they going to terminate on their own? And is there any conditions that could cause the threads to not terminate? In this particular scenario, I know there's a way that the threads might not terminate because I have deliberately introduced that error to the threads. Now, I want to talk about this little chunk here because it's a bit odd, and it has to do with the test setup. So everything inside of here Like all of that code that I just highlighted, basically from line 29 to 92. Actually, I would say from 29 to 76 would be more appropriate. That's the core of the program. That's what's doing the actual counting. So that's revving up the threads, setting their ID, or creating the instances, setting the IDs, revving up the threads, and then winding things down once once all the counting's been done. And so if we didn't have this specific scenario where I was forcing things to run multiple times to try to force the error, that would be the program. But as you've seen, it can sometimes take many, many, many runs of the program, so to speak, to get our race condition. And so that's why I've got this outer while loop starting with line 24, which is basically saying, hey, keep doing this task over and over and over and over again until something goes wrong. Okay. So again, coming back to line 81. So what I'm doing here is cleaning up because I found while I was running this, especially when I was running it and I had the bad luck of having 20, 30, 40,000 cycles before an error occurs, it was actually causing problems with having far too many threads spun up too fast, and also too much information being in the console and causing just clips to start spazzing out. And I actually locked the clips up a couple of times. So that's why I've got this in here. I am explicitly releasing the references to the object. We don't talk a lot about memory management in Java, but it is important to understand it. That when you create an object, it's going out into your computer's RAM, grabbing a chunk of memory, and using that chunk of memory to hold all the information needed for that object. And then behind the scenes, Java has this thing called the garbage collector, which is constantly looking for chunks of memory that do not have a valid reference anymore. So like once a variable goes out of scope, or if I've explicitly set something to null, then that chunk of memory no longer has a valid pointer to it. And so the garbage collector knows, oh, okay, I can free up this memory. There's a lot of crazy, complicated logic that goes into controlling this. Generally speaking, the garbage collection process in any managed memory language, whether it be Java, C# or whatever, is not something you should ever worry about. There's only very rare specific scenarios in which worrying about the garbage collection is warranted. So what I'm doing here is I am explicitly releasing the reference to the memory that these instances pointed at, and then prodding the garbage collector. It's like, hey, do you want to maybe do something? It might not actually. This line of code is not actually guaranteed to do anything. It's literally just poking the garbage collection process and saying, hey, take a look at memory, see if there's something you want to do. I can't actually force it to do something. And then, like I said, if it ran for much more than 20,000 cycles, I would start getting problems. So I've got this little safety thing here. It's like, hey, if you've ran for 10,000 times, just stop. All right. Confused yet? Good. I'm going to confuse you more. Some interesting things can happen when we do some other tweaks. For example, we noticed that when we run this, we can get wildly long stretches Like, yeah, to the point where I just momentarily got confused there. You can have wildly long stretches of just one particular identifier or one particular thread running. It's like right here, looks like the one goes from 312 all the way to 365 before we have a 3 bump in there. And 2, okay, yeah. There's 2 right there. 223. Oh, no, this is... I'm not even sure how 2 got to that number so soon. Yeah, it's just, I don't know. It's just weird. It's like we can see that there's like really long stretches of one thread dominating. And so you might think, okay, for whatever reason, sometimes you're going to want to tell a thread to pause. By the way, I'm going to use Control// to toggle those comments off. Now, thread.sleep is how you tell a thread, it's like, hey, chill out for a moment. The thread's still alive. It will still read as a living thread. It's just you're telling it to say, hey, for the next whatever milliseconds, however many milliseconds you want to put in here, just don't do anything. And now that's upon the operating system and all the other black magic, dark sorcery stuff that goes on behind the scenes that makes threads work. It's that stuff's responsibility to actually manage that. So I'm going to say thread.sleep, and I'm just going to have each thread sleep for a random amount of time between 1 to 10 milliseconds. And as you can see, this is mandatorily encased in a try-catch block. Like, you must have the thread.sleep must be in a try-catch block because you must be able to catch the interrupted exception if you call interrupt on a sleeping thread. Which, of course, if that happens, all I'm doing is breaking out of it. But this makes something interesting happen. First, it's going to slow things down drastically. And second, it guarantees it will lock up every single time. All of a sudden, we've gone from anywhere from 30 to 9,000 or more cycles before we lock up. Every single time I run the code, it locks up. The race condition is triggering. You can see there's a lot more. It is going 1, 2, 3. Got 3, got to go twice there. 1, 3, 2, 2, 3, 1. It's like, it's a lot more interwoven, but almost without fail. Like, I have not had this go for more than one cycle out of many, many times running this code. And this is where sort of the complexities of this comes into play, or threads come into play. But I can actually, it's fairly easy to explain why this guarantees the race condition will occur. Whereas if you don't sleep, the race condition will eventually occur, but who knows how long it will actually take. Because when it's running full speed, as long as all 3 threads are in this portion of the code, it will work correctly. For the most part. So, actually I said that wrong. As long as all 3 threads are on this line here, it's not going to break. So thread 1 comes in, increments the value, does the print, does the if check. As long as you're not hitting this line right here, it's going to be fine. I apologize for the sort of somewhat disorganized way I'm trying to explain this. But even for me, someone who has dealt with threads for many years, it still requires a lot of concentration, mental effort, however you want to phrase it, to keep track of what these crazy things are doing. So this is the line that basically causes the problem, or one of two lines that causes the problem. Now, if this gets incremented at the wrong time, then the code breaks. The problem here is that by having all of the code always catching right here, you guarantee the problem's going to happen, because all three threads, are going to hit this and then go to sleep. And then very close to one another, because 1 to 10 milliseconds is a negligible amount of time as far as CPUs are concerned, that pretty much guarantees that at least 2 threads are going to hit this line at the same time. And if 2 threads hit this line at the same time, at the wrong time, program breaks. But you are pretty much guaranteeing that this will always be the case for every single number. And so, thus, because I put in this little sleep thing, besides slowing down the code, it causes the race condition to trigger every single time. Now, your assignment for this week. So a couple of things. First, the assignment for this week is going to be very simple. Change a single character, and I do mean that literally. Change a single character in this file to ensure that it will never lock up again. There is a single character that you can change, and I do mean that very literally. Whether you change it, delete it, or add it in, there is a single character change that you can make to this file that will ensure the race condition doesn't cause an endless loop. It will never trigger the check here of value being greater than target plus 10. So there's a single change that you can make to ensure that the program never locks up. That is your assignment for this week. Next week, the assignment is going to be threading your prime check code. Now, that one will be interesting because, one, you are going to have to use threads, at least 2 threads, to do the calculation up to 2 million. Don't start on this assignment yet. I'm still working out details on this, so don't start on this yet. So you're going to be calculating all the primes up to 2 million, probably. This also means that some of you are going to have to redo your code entirely, because the way some of you did this, you can't actually complete the assignment because of the way that you did your arrays and stuff. If you go up to 2 million, your code will break. It might be 200 million, but whatever. The number will be high enough that it will break some of the code. Also, your code was written, everybody's code, mine included, was written on the assumption of a single thread of execution. Some interesting things come into play when you're trying to bring data back together to be able to, merge things back in and have the data presented in a reasonable fashion. So that is what we are working towards. So again, to reiterate, this week's assignment is to make a single change to this file that will cause the race condition to never happen. A single character change to this file to ensure the race condition never happens. And then next week, the assignment will be to multi-thread your prime check code, so that way you can use threads to find all the primes up to a very large number. With that, have fun finding the one character, and I'll catch you on the next video.